Okay, let's get started. So today we're going to be addressing this Bayesian point test. So same setup as last time. I've got some IID data coming from this model, and I want to infer this. I'm going to say this is known for now. If I didn't know it, I would average over it. Using a gamma probably, and I would induce a t-distribution. And so we want to test, is theta equal to theta naught? Now I want to be very specific about this question. Is this really what we're asking? Is this what humans want to know? Is theta equal to theta naught? Precisely, or is it something different? So keep in mind this is one point in a continuum. What do you think the chances are?
Zero.
If I do it on a computer and I set that thing to be like theta naught is equal to 0, then I know what it is. And so I think that it's something we can demonstrate all the time in simulation setups. But my real question is does this happen in reality? And so I'm not arguing philosophically over whether or not theta has a true fixed value. That may or may not be true. Populations might not be IID, but maybe they are. So I'm not going to make those arguments. But my speculation is when you're dealing with this problem, you're not exactly wanting to ask this. Right here, you want to ask, is it close? And so Bayesian's very specific about that. And they're going to make you define in some sense what you mean by what close is. Let's go back to what a classicist does, or kind of the stat 101 type analysis. Remember what happened when we discussed this problem and we came up with a standard deviation. So we came up with a z-score that was 1.97. So just over the 1.96 threshold. So we clearly reject, right? But as n went off to infinity, we ended up saying that true theta was theta naught. Remember that analysis? So I looked at this. Dn, x bar n minus theta naught, absolute value, sigma over root n. So I was looking at this and I said, what does this mean is a function of n when it's 1.97? So this is what it's saying. The interpretation is the distance between x bar and theta naught is 1.97 standard errors. Okay? So I'm trying to think about what happens as n goes off to infinity. This thing's easy to analyze. It goes to 0. This thing must also be going to 0. If it were something fixed, this would not happen. You wouldn't have 1.97 in the limit. And so this also has to be going to 0 if this is true. So I'm just thinking in the limit what it means for something to have a z-score of 1.97 if n was infinitely large. And so what does that mean for this to be 0? It means x bar n was going to theta naught. But I know what x bar n also goes to by the central limit theorem, or whichever law of large numbers you want to consider. The weak one, the strong one. I know this goes to true theta. Goes to the truth. So the truth is theta naught. So central limit theorem says x bar goes to the truth, which is theta. And so if it's going to both of them, then these things have to be equal in the limit. So this is just a limiting train of thought. And so Neyman and Pearson would still say you reject this. And they would come back and they would argue. Like, okay, that's a nice mathematical parlor trick you just did. Blah, 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 blah. I don't care. Because this is still 1.97 times standard error away from theta naught. And so it's 1.97 times in terms of a relative, in a relative sense. Keep in mind, this thing is very, very tiny. And so in an absolute sense, just this part, how close is it to theta naught? As close as you want, epsilon, and make that as small as you would like. And so the question is this what a human wants? Do they want to hear your 1.97 times the standard error weight from your null hypothesis, but that distance is epsilon in an absolute sense? And so let me give you an example. So imagine I have a coin. Maybe I do. Maybe I do. I've got a quarter right here, and I ask the question, is p equal to p naught? And I'll even wager a guess. I think 0.5 because there's two sides and I want to know if it's fair. Let's say I flip it a bazillion times. And I compute a z-score, I invoke asymptotic normality, but I can control n and I flip it a zillion times. And so I like the normal approximation. And I notice that my z-score is a little bit on the big side. My p-value is on the small side. So it's 0.00000000001 is my p-value, because I flipped it a bazillion times. As close to infinity as I could get. Okay, so we can imagine I do that, and I say, no, it's not fair. And then you come and you ask me, well, what's the frequency of the times I got heads? And I say, well, it's 0.5000002. You say, well, I thought you said it wasn't fair. And I say, it's not. I can detect that difference between 0.000000000 and 0.00002. So I can detect that small difference. And that's within the standard error. And so that's when people say, well, statistical significance never was supposed to mean anything practical. I say it that way, but you've heard this before. Statistical significance and practical significance are two different things. And so it depends on who you're talking to about statistical significance, but in that Stat 101 setup, this thing that most people do, and they look at a z-score or something like it, they really are asking this question, is it exactly? Is theta theta not? So that is the question. And they're being quite strict about it. And so Bayesian's going to loosen that up, and they're going to talk about close. But let me just tell you the answer. Let's imagine I'm not doing this on a computer. I'm not simulating it. I go out to some data. I go out, I collect some data, and I try to answer this question, is theta theta not? Let me just help you out. It's not. So in any real problem, the probability of you picking that right number out of the continuum is, I just don't believe you picked it. So coins are not going to be 0.5. In fact, coins are pretty far from 0.5. You know what they are? Quarters on average. It's in most Stat 101 books. I'll show you the frequency of flipping coins. About 5248 tails. And so tails land a little bit more, about 2%. We don't even care, right? You've never noticed this. How many times have you flipped a coin to make a decision? We've all done it, right? Has anybody never done that? Like, let's flip. So everybody's done it, right? And what did you pick? I don't know, you just made up a number. You just, like, in the spur of the moment, you picked something, right? Because you thought it probably didn't matter. And I do that too. So it's like, but you're giving up 2 wins out of 100. 100 times, out of 100 times you've done this, you could have won that bet 2 more times on average. You didn't even notice, you didn't even care, so it's not within your practical significance to even notice this. And so, I don't think the question is this. I think the question is close, but we have to define close. And the old setup, the classical setup of testing this is they're asking this specific question. And I'm going to help them out. The answer is no. If you go get an infinite amount of data, you're going to reject because your hypothesis is wrong, your model's probably wrong. You're going to reject for some reason. And so all of that is a bit of a problem. So I think this is the contentious test in statistics. I think the one-sided test turns out to be pretty reasonable the way people compute them. I'm not too opposed to those. And it has to do with this simple thing that if I ask what's the probability of the alternative or the associated p-value, the measure of evidence, I take 1 minus my old p-value of a one-sided thing, but we don't do this here. And so it doesn't have additivity properties, it's not a measure, it's not a probability of the null hypothesis, it's not any of those things, the p-value, and the Bayesian wants to construct that. But they're forced to answer this closeness question. So the prior that we use to test this looks like this. And pretty much all Bayesians will use this setup. So a Bayesian will use a point mass prior Some people call these point mass mixture priors because they are mixtures. And they look like this. So pi theta is going to have a discrete component. Delta is just the indicator function. It's a 1 if this statement is true, and a 0 otherwise. So theta is equal to, this is 1 if theta is equal to theta naught, and a 0 otherwise. So it's a switch. Plus 1 minus the null mass on the alternative space. So I'm just going to write that down like this. Pi HA theta. So this is the alternative prior.
Which we don't know the distribution of, right?
Well, it means what, it depends on what you mean by no. I can pick something
No,
for
I
you.
mean, because usually we say that under the no, we have the uniform, but under the alternative we don't know.
We need to study the properties of this creature.
Yeah.
Right here. That's what we need to do. So that's what the next couple lectures are going to be about, is studying the properties of when we change that. So this right here is the null prior. If I consider this as continuous sort of function with an infinite blip and I integrate over it, it turns into this integrator, this indicator 1, 0 right here. And so I might think of this as a measure. And so, and mathematicians will tell you that's okay to do. So, in general, a Bayesian will use this sort of mixture prior for testing two hypotheses, comparing them. A Bayesian will use a mixture prior and it looks like this. Pi theta is going to be pi naught. This will be pi h naught theta plus 1 minus pi naught pi h alternative theta to compare hypotheses. So in our case, our null only takes on 1 point, so I don't have too many choices on how to pick the null prior. But in general, if we're testing one-sided interval against the other side, then I'd need to put mass on each of the corresponding sides. Okay, so the measure of support for pi h naught is going to be the support in the null region. And I need to put a prior over that. Same thing with the alternative. In the point mass mixture case, I can smear mass on the null hypothesis in a lot of different ways, and it always looks like this, no matter how I get it. So it's just taking on value at 1 point. It has to integrate to 1 because it's a measure itself. Voila. There's only one way to do it, the indicator function. So this is a general setup. We'll come back around for this later. And so what does this specific point mass mixture prior look like? It looks like this. So here's the alternative. Pi h alpha and then I have the point mass somewhere. Maybe right there. Now I drew it a little bit funny. So I've kind of drawn it in general. So I kind of maybe assumed that it looks like a bump where it puts mass somewhere. We might have to talk about where the alternative places mass and how to calibrate all that. So why don't we just discuss that right now? So let's just consider an example. Let's consider this example, same example, and let me just ask a question. Question: how would you choose pi naught? For my prior, I've got to specify it. Some people will do funny things where they'll put a binomial distribution over that, and then they'll use a beta hierarchy to generate something so that they're not too sensitive and they can kind of move that around. And so they'll generate p out of a beta, and then they'll draw the ones and zeros. I don't generally do that, but I think that there's good reasons to do that. And in Monte Carlo land, there's very good reasons to do that. That you have this switch turning on and off. That's the Malik and Quo paper that told us to do that. And I have used that setup. We'll come around to the Monte Carlo implementation soon. But just how would you choose this? In this other hierarchy, I'd still have to ask, how did you pick alpha and beta in your beta hierarchy? You'd probably make them equal to each other. But what would you pick? You're just rational human beings. You want to test these two things.
25.
25? Why?
To represent that equal chance of that or not, maybe. Yeah, just to start with.
Yeah, because of obviousness, right? I don't know. I don't want to weigh one over the other. So most people pick 0.5. So 0.5 is the most common, is typical. What I kind of like to do with this sometimes, and I wish I had an app to do this, so if anybody wants to make me this app, that would be great. But I wish I could have a little slide bar on it and show how the posterior probabilities, what we're really after change, is a function of pi naught. And so I could just slide that thing around, and somebody might say, hey, I need a probability, posterior probability of the null to be at least 0.9 before I'm willing to go with it, before I'm willing to make a bet on that thing, whatever a bet means to you, either a physical bet or I'm willing to publish. And you might say, I can get that 0.9 even if pi naught was chosen to be 0.001. That would be extremely strong evidence that the null was true. That if I were able to steer this thing and say, the prior probability, your prior probability would have to be 0.001 to get me below a posterior probability of 0.9. That'd be pretty convincing, right? Did you guys understand that? The rationale? So my prior mass was 0.001 and my posterior mass on the null was 0.9. And that would probably convince you that, yeah, even if I bias this thing, if I had strong reason to doubt something, the evidence still suggests that the null is true. So I kind of like to do that. How far could you budge the prior probability before you thought it was not significant to you? So I believe in personal probabilities and how you calibrate these things, and I think about these things on spectrums, and I think with computers now we can demonstrate that stuff. Christina?
So if our H naught is just theta is equal to theta 0, it's not like a range. Is it actually practical to say that 0.5 is our prior for H naught, and for the whole continuum we're also putting 0.5?
Yeah, I understand that what Christine's saying is that the whole continuum has way more values in there. We're going to have to be a little bit more specific about what we're really testing. Again, the Bayesian's only testing closed things. And really, the alternative prior is what calibrates all of that. I'll show that to you eventually. So let's come back around to that question. But I understand that I'm comparing these two sets, and one is infinitely bigger than the other. So is that fair? Maybe. Depends on how much you weigh that thing. And so, but good question. You're allowed to move this thing around. Let me go to an example, just real quick. Somebody does exactly that. So does anybody know who Jessica Utz is? I think I've mentioned this in my inference class. So she's a statistician. She's a fellow of the ASA. So she taught me a class when I was at University of California. So I took one of her classes, and I saw her as recently as 2 weeks ago on Netflix. And so I was watching some documentary on ESP, and she always pops up. So she's done a lot of ESP research. And she says that the evidence for ESP is so strong that even, like when she goes in and she does these psychological studies with people, and she says, what's the probability that you believe ESP exists? And they'll say things like 0.0000001. No way. People are really strong about this, one way or the other. And the people that believe in it, they're really strong too. And she ends up saying, well, the posterior probability that things would have just happened like this by chance, is really astonishingly low. That the posterior probability that there's something going on with people's mental connectedness is very, very strong. So she ends up equating this, and every time I see her talk about this, is she says that if the evidence that was required to convince somebody that ESP worked and was a real thing, not that everybody has it, if that was the standard bearer for evidence that we would need, we wouldn't have any medicine on the shelf, including aspirin. And so the evidence that ESP is a real thing is astonishingly high. So this is how they do it. They end up looking at, so these are their studies, if you're just kind of curious about this, they'll look at 4 different paintings. They'll have these 4 different paintings. Somebody will be sitting in a room, and they'll end up trying to telecast, or whatever you call this thing. So telepathy. I'm not a big follower of this. I just think it's interesting. And they'll try to project like a particular image and then have somebody draw it. And they'll focus on one of the images, and then they'll go to a third person. They'll show them an array of images, and they'll have them match the person's hand-drawn image to, one of the images that was handed to the people. So they'll have that collection of 4 images. And they should be right, on average 25% of the time, something like that. And the numbers are total mismatches. And there's some people that exhibit strong non-ESP skills that they just don't have it. They're worse than random because they don't believe it so much. It's kind of a weird thing. Anyway, lots of questions about that. Some people do move this thing around. I'll hand out a paper later on Jessica's work. I think it's pretty cool. But she basically uses this analysis to try to convince people with very small that you can get strong evidence that ESP exists. Okay, so I think maybe this is an easy question. So here's another question. How do you choose the alternative? What would you pick?
You could center at X bar.
Maybe you center it at X bar. I would accuse you of double dipping your data if you do that. Just keep in mind that, let's just go back to estimating theta in general. If you were back in the estimation thing, if you used a prior and you sent it at X bar, you would end up putting a lot of mass right around that thing. So you would be kind of double dipping your likelihood function. It would reduce your variance. So I probably wouldn't go grab data quite yet, but you're on to something. So center it at something. But how would I even pick the functional form of this? What would you do if you had to do this? Imagine yourself in the 1950s, you're the first person to stumble across this, what would you grab?
Are we doing our normal example?
Yeah, we're still on this example.
A normal, maybe?
Yeah, maybe a normal. And so I think that's what people grab first. So a normal.
Maybe center at the null hypothesis?
Maybe normal, and I'll call this theta, HA. and I've got some variance. Okay, so Ben said, and I think this makes sense to me, that if I'm going to pick something symmetric, where would I want to center it? Am I really weighing the left side more than the right side? And so there's good reason to think maybe you should center it at theta naught. So I kind of like that. So maybe choose theta HA equal to theta naught. So this is just symmetric on each side. So you could come up with a good symmetry argument for doing that. Why would I center it anywhere else? So let's just think about this. Let's imagine theta naught was 0. And I picked theta HA to be 10,000. So if I don't think it's 0, then I think it's 10,000. Doesn't make any sense. So it probably should be close to theta naught. So why would you pick anything else? So last question, how do you pick psi squared? We've just been perfectly human about this. Ben's answered both times. He said 0.5 and then maybe pick theta HA to be theta naught, and somebody gave us the normal prior. So we're just trying to think our way through. Later on, we'll check the repercussions of all of this.
If you set it equal to 1, would that
Yeah, so what does it mean, right? Why 1?
standard one? I mean, you're for human reasons.
What's your human reason for 1?
We like 1.
You like 1, right? 1's like a special number. So I'm not sure what it means exactly, especially if x bar can be anything. So, you know, if x bar isn't standardized, I don't know that 1 makes much sense. So if it's standardized, maybe I can come up with reasons for it, but I haven't standardized any data.
If you think,
I know sigma squared, yeah, so that's an interesting, compelling thing. Maybe I should plug in sigma squared, and I would give my alternative kind of the uncertainty of 1 data point. And that's what Melissa's saying. It's the first time anybody's ever said that to me. So I think that's actually something that you might do in this case, and we have to talk about the repercussions of that. So I think the answer on this is a lot harder to rationalize. So it's unclear. I'm just going to write it down. Let's just leave it as a function of this and work out all our analysis and see what bearing this has on the analysis. Now I'm going to give you a hint. It turns out our answers aren't too sensitive to this. They're not too sensitive to that right here, but they're extremely sensitive to this. And so the harder question to even like intuitively rationalize is the most sensitive parameter in the analysis. This is a big problem. So let me just write down what we end up doing.
so one idea, you could base it on your desired relative error if your theta naught is not 0.
Yeah, maybe. Maybe you could calibrate it to some form of relative error, and you would have to come up with your reason for calibrating it. And so I do like that. So let's come back around to it. It's got to mean something to you. So maybe if you're a physicist or something like that, and you're trying to detect things, and you kind of know what machine tolerance is, you could build that in as your alternative variance. Let's come back around to it. So the posterior probability for H naught, well, I'll just say the posterior in general, is, and keep in mind, X bar is sufficient for theta. So I'm going to write my likelihood down like this. So my likelihood function on theta given x is going to be proportional to e to the minus 1/2 theta minus x bar squared over sigma squared over n. So I didn't use the product form of everything. If I producted everything together, it would be proportional to this. If I didn't know sigma squared and I did this, I just made a huge mistake. So in our prior, looks like a point mass prior. So our posterior distribution just looks like this. I'll say proportional to e to the minus 1/2 theta minus x bar squared sigma squared over n times pi naught delta function plus 1 minus pi naught, and then I'm going to have my alternative prior. And for now, let's just leave that general, but you might be thinking the normal conjugate prior because you could do the math, and well-calibrated psi. We don't know all the repercussions of that, but we know to be weary at least. And where would I center it? Maybe theta naught. Let's just leave it as a function right now. So that's my posterior. Of course, I got to normalize this thing. So how do I normalize it? Just integrate over everything in the numerator. Psi squared over n, pi naught, delta function, 1 minus pi naught, alternative prior.
Why are we normalizing it since we're taking the function?
Well, I want to know what's big and what's small, might be the answer. This number is supposed to live between 0 and 1. So if I want it to mean something to you, I probably should normalize it. So this whole part right here, where I'm integrating between negative infinity and infinity over the whole region of theta, I could just write this down as pi x bar. It's just a function of x bar. It's the marginal distribution of x bar. So let me just ask a question real quick. This should be obvious. What's this? Probability of h naught given x bar. It's the posterior probability of h naught. We might write this like this, pi theta element h naught given x bar. Just want to remind you this thing's a probability. It's a discrete thing. There's only two things, they add up to 1. What is this? Can you tell just by looking at this equation?
You get only
Just the ratio of this numerator, but you plug in for 0, right?
Right, that's right. You plug this thing in. So what you do is you integrate it over theta naught. So this thing just looks like this. Integral of my posterior probability. Oh, and apologies, that's not prior. That's conditional on data. I have data in there. This is just going to be pi theta given x bar d theta, where I'm going to integrate in the null region. This is just theta is equal to theta naught. So it's a pretty easy integral to do. I integrate over this. When theta is equal to theta naught, that turns on to 1. Otherwise, it's 0. And when I integrate this at one point, this is a continuum, I get 0. And so this is just going to be e to the minus 1/2 x bar minus theta naught squared, sigma squared over n, pi naught over px bar. So I just plugged in the theta naught. The other one's harder. So if I want the probability of the alternative, HA given x bar, this is going to be equal to 1 minus pi naught integral e to the minus 1/2 sigma squared over n. Then I've got my prior. P HA theta. So I just need to integrate this whole thing. I can integrate it even including theta not in there because the measure on that is pretty small. Ben?
Question, could you just go 1 minus probability of null?
Yeah, absolutely. So seems easier to just do that. So Ben just said this, probability H naught given x bar. So we could have done that. But keep in mind I did have to solve this integral to do the denominator. And so any which way you're going to have to do that integral. And this is the big beast calculation of any sort of Bayesian hypothesis test, is doing this integration. I'll give you a paper soon on lots of high-dimensional computational strategies for doing this.
The denominator is x bar, right?
What's that?
The denominator is p of x bar.
Yeah. X bar. That's right. So that's what it is. Bayesian's kind of like this because you have kind of a tug of war on the alternative and the null. So the alternative really influences this. It normalizes everything. And so everything's very comparison. I also want to point out, let's imagine in this whole calculation, you didn't like this assumption that everything was normal. So you think this is an approximation. Look what happens in the numerator and the denominator. I have all those e's down here as well. And so any error I make in the numerator, I also make in the denominator. And they're kind of balanced because they're coming in a ratio. And so everything in the Bayesian sense is comparative. And so that tends to give nice properties. Okay, I want to teach you about a couple quantities that Bayesians use once they calculate all of this. So note, probability H naught given x bar over probability HA given x bar is called the posterior ratio. For obvious reasons. So most Bayesians don't use this. They usually don't report this. Some people will come in right away and say, well, I don't like your influence of pi naught. And so I want to remove that from the analysis. So some prefer, I'll say most prefer this. Reporting the probability ratio of the null, posterior null, to the posterior alternative. And they usually like to divide out their prior. Too many questions about the prior. People will ask about that. Now, if you picked it to be 0.5 and 0.5, it flushed out anyway. And your posterior ratio and your prior ratio are the same.
Wasn't it this debate in the prosecutor's fallacy whenever we were taking the ratios, or no, in our first homework? Where we had to compare the posterior ratio with,
Well, maybe you did that sort of calculation to isolate what, the implied priors were.
no, but I mean, if you had to compare those two ratios, wouldn't that kind of contrast what a Bayesian thinks of it?
That problem has a different take-home message. That problem has that if you fool yourself and you apply the prosecutor's fallacy, your priors on innocence are not very good. Your prior on guilt is way too high. That's the take-home message. If you work through a ratio that looked like that, I could see that happening. But I don't know if they exactly compare because the prosecutor's fallacy is still a fallacy. We shouldn't apply it. That was magically flipping the conditionals. But has anybody seen this quantity before? Posterior odds. I'll just say it to you in English. Posterior odds divided by your prior odds. This is how your odds change once you see the data. That's kind of a nice thing. So the denominator, your prior odds, that's what you thought before you saw the data, and it's how your odds change relative to your prior odds after seeing the data. Kind of has a nice interpretation. So once I see the data, how does it compare to before I saw the data? So this is called a Bayes factor. And this is what the Bayes factor is. There's another way to write this. I could have written it like this as well. And they're equivalent to each other. You might see this instantaneously, or it might give you a couple lines of algebra. Bayes factor also looks like this. Integral, I'll write down p x bar, given theta, I'll write it in general. For our null testing case, this is delta function. For other cases, this could be something arbitrary. I don't need to use x bar as the sufficient statistic, so in general, this would just say data. But the Bayes factor looks like this. P theta. Where do I integrate? I integrate in the null region, in the numerator, and then the denominator, I integrate where the alternative has mass. So this is just marginalizing. So I can write it down like this. This is just going to be p x bar. And I might write it down like this, conditioned on the null. And this is p x bar, conditioned on the alternative. So this is a marginal comparison of the data. These are equivalent to each other. If I wanted to flip this thing around, just think what I have to do to turn this thing into a posterior. I'd have to multiply by pi naught right here. I'd have to multiply this by pi alternative. It would flip them around. The normalizing constants would cancel. That's px bar in both cases. And I'd need to divide those out to have the exact same equation. That's this representation. These are equivalent to each other. They're the same things. But two very different ways to think about everything. So this is the ratio of the margin of the data. This says to me, how well does H naught support the data compared to how well H alternative supports the data? On average. So these are average comparisons. Has anybody ever seen a model selection tool that statisticians use? They kind of smack of this. Yeah, kind of.
Or like a likelihood tissue.
Ah, I like that. Yeah. So one can be derived from it. So it's likelihood, it almost looks like the max likelihood ratio. Recall, the max likelihood ratio a lot of non-Bayesians use this feature. They look at this. Maximize theta in H naught, the likelihood. I'll just write my data as x bar. In general, you would just write data there. Theta in the alternative region. A lot of people compare these things right here. The Bayes factor is similar to it. So the Bayes factor is an averaging of the numerator and the denominator. And The max likelihood ratio is a maximization of both of those things. And if this posterior is very, very tight, so if I saw a lot of data and it were tight, the same thing in the alternative space, if they were tight, then the integration and the maximization would be similar to each other. Of course, if these are very diffused, this surface and this surface is very diffused, then these won't correspond to each other. As n gets bigger and bigger, then this usually tightens up, and this tightens up somewhere. And so when n is big, they tend towards each other. So I'm not sure which one is better as a real human diagnostic. I have gone around, I kind of grappled with this question for a long time. What do most people want to use? Like when scientists think about things, do they think about when they're supporting maybe their null hypothesis, how the maximal, whatever my best guess is out of that whole model class, how it compares to my best guess in the alternative model class, how they compare to each other, versus on average, how the model classes compare to each other. So I've gone to a lot of scientists and I've asked, which one do you prefer? Without studying any mathematics. So I think it's a very human question, is what do people want? More people have responded to me, they prefer the max likelihood ratio. I want to look at my best guesses and compare those. So that's just some trivia. I also want to point out, from the Bayes factor, we can compute this, the probability of H naught given x bar. This is always this. 1 plus 1 minus pi naught, Bayes factor, inverse, all invert. And you might be able to see that relationship in your head. Keep in mind the Bayes factor is a ratio, so I can just write this down like this. So this would just look like 1 over 1 plus 1 minus pi naught, Bayes factor inverse. If I multiplied everything by the Bayes factor inverse in pi naught, this would look like this. Bayes factor, pi naught, Bayes factor. All equivalent things. What's in the denominator of the Bayes factor? The alternative. So if I multiplied that all the way through, I'd kill the alternative in the denominator here, the alternative here, and it would show up right there. This is just Bayes' theorem. So I'll let you carry it home by substituting in the Bayes factor definition and seeing this is just Bayes' theorem for computing this. So if you give me the Bayes factor, I'm probably going to compute the posterior probability with it. And I'll make my judgment off of a 0-1 scale versus a 0 to infinity scale. So there are guidelines people give you for interpreting the Bayes factors, and I would say your guidelines that you can come up with in your head are as good as the suggestions made by the greats of statistics. I kind of like numbers like 0.9, things like that, things I can convince people of, but who knows. So I want to come back around next time. I want to plug in my alternative, my conjugate suggestion, and see how all these functions, the posterior probability, the null, the Bayes factor, how they vary as a function of those hyperparameters in our alternative. And I'm going to give you very unsettling news that those parameters matter a lot. So I will give you an interpretation that the alternative variance, that in some sense is the distance you need to be from the null before you're willing to reject it. So if you take that variance and you make it very big and you make that prior very flat, you're saying you need to be infinitely far away from the null before you're willing to reject it. And that's a huge problem. So you cannot use reference type priors there. And so it just doesn't work. And so you have to come up with something more subjective. And so I'll tell you lots of possibilities for it, but there's a lot of debates there. So the Bayesian's going to force you to define what you mean by close, but not everybody agrees on which metric to use, is the bad news. That's it for now. So thanks, you guys. We'll do a review tonight.